So, layout. First, background. My interest in plasmonics began when I was a graduate student at the CREC. My first work in the field was the development of wet chemical route to prepare LSPR substrates, that is about 50 nanometer thick gold film, usually prepared for vacuum dry deposition. We also developed a method to prepare fractal plasmonic nanomembrane via diffusion limited aggregation at the air-water interface. Then, when I was a postdoc at Weizmann Institute and UW Seattle, I got into nanoelectronics and moved my interest in plasmonic nanostructure into multifunction all-in-one nanostructures for multimodality imaging. My research group at CREC continued to work on plasmonic nanostructures and their application in biosensing, nanocatalysis, and nanoelectronics. We are also interested in glass nanopipette-based nanopore and sensing applications. We developed a film method to prepare gold nanofilm, decorated glass nanopore, and try to shrink nanopore for DNA translocation and structural analysis, and also single-cell biosensing. Our group also interested in electroanalytic chemistry and explore electrochemistry for in vivo biomedicine. Very recently, we report green, efficient, and precise hydrogen therapy of cancer based on in vivo electrochemistry by using Chinese acupuncture on needle as electrode and working under 3 volts of applied voltage. Okay, back to the topic today. Due to unique property of nanoparticles, the emerging field terms plasmonics has witnessed rapid development in diverse hot fields of research, since it can merge photonics and electronics at nanoscale dimensions. So far, various plasmonic nanoparticles have been widely applied for biosensing and nanomedicine. Also, the marriage of plasmonic and analytic science have enabled a new era of nanobiotechnology, push forward the development of nanomedicine and make science methodology more sensitive and smart. Next, I will introduce some work on designing plasmonic hybrid nanostructures for biosensing and imaging. Previously, our interest in plasmonic nanoparticle focuses on prepare multifunctional compact gold nanoshell. Here shows a method by mimetic method to prepare ultrathin gold nanoshell on the surface of core materials by using poly-L-histidine as a molecular template to control the deposition of gold film. Due to the presence of polymer gap in between the core and the shell, the fluorescence of quantum dot can be reserved, so it can prepare as a multimodality imaging nanoprobe. Also, the core material can be changed to magnetic nanoparticle and also soft liposome. More importantly, based on magnetic plasmonic unoxide gold calcium nanoparticle, we develop a new biological imaging modality called Magnetomotive photoacoustic imaging. Since it suppresses region not susceptible to a magnetic field, it profits markedly improved contrast and specificity. So it is envisioned very promising for potential clinical use for early detection of cancer. Our group also prepared the smart plasmonic glucose nanoprobe. Recently, we prepared enzymatic gold silver nanoshell by depositing glucose oxides on the surface of silver gold bimetal nanoshells. The enzymatic reaction will result in the dissolve of silver from shell, resulting in nanoporous nanoshell. In the process, a significant LSPR shift occurs, so it can be used for sensitive optical glucose sensing and also in situ enzymatic activity detection. Since cancer cells usually have high glucose uptake levels than normal cells, so the sensor has been exploited for targeting free cancer cell screening and selective cancer cell killing. Our group also interested in prepare some smart plasmonic source nanoprobe. For example, we prepared pH and cytochrome C dual responsible nanoprobe and used for real-time monitoring cytochrome release and cell acidification in apoptosis during electrostimulation. We also use such smart nanopore to reveal molecular stress response difference in hypothermia cell death and ES induced apoptosis between cancer and normal cells. Very recently, our interest in nanostructure moved to two-dimensional gold nanoparticle-based nanomembrane. Here show nanomembrane prepared by gold silica core nanoparticle due to well-defined core structure and arrangement. The electromagnetic field has been intensified in the film. Also, the cross-section and scattering intensity have significantly been enhanced, so it shows over 1,000-fold E-cell enhancement in the palladium ruthenium E-cell system. We further built prostate-specific antigen E-cell immunosensor. Such sensor showed good selectivity, reproducibility, and very low detection limit for PSA detection. Next, I will introduce briefly our work on plasmonic hybrid nanostructure for catalysis. We are interested in nanoengineering of plasmonic nanoparticles for photocatalytic applications. For example, we develop an all-solution road to prepare silver-gold porous nanoshell by tuning porosity of the particle. The catalytic activity in the case of 4-nitrophenol reduction to aminophenol can be well tuned. Also, we prepared gold core platinum shell concave nanocarbons. It shows much better electro-oxidation of ethanol than commercial black. We also prepare some hybrid nanocatalysis for HER or OER in water. For example, we prepared quantum dot gold core satellited nanoparticle and also bacterial rhodopsin gold silver nanoparticle-based nanohybrids and use the plasmonic enhancement and combined with by function of protein to enhance HER. We also, since plasmonic nanostructures have good photothermal conversion ability, we prepare some like plasmonic colored serum and also prepared platinum gold titanium dioxide decorated plasmonic wood carbon and use them as floating membrane for high efficiency solar steam evaporation and also further degradation of tetracycline. Very importantly, during the experiment, we also revealed some unusual plasmonic properties So in the case of isolated self-gold bimetal nanocluster, we observed the anti-galvanic reduction phenomenon. By systematic SPX and CV study, we profit direct electrochemical insight into the mechanism. So the driving force of anti-galvanic reduction was found due to the extraordinary change in the redox peak potentials of small-sized metal nanocrystals, typically smaller than 2 nanometers, caused by the coherent discrete energy gap of the particle. In the model reaction of 4-nitrophenol to aminophenol, by using gold silica calcium nanoparticle as catalysis, we revealed a long-range plasma field plasmon-electric effect on catalysis. The plasmon-electric effect was found first by Professor Edward at Caltech in 2014. We found that also in our system, also the gold nanoparticle has been encapsulated by compact pinhole-free silica shell. The reaction occurs when shell thickness smaller than 2.5 times radius of gold nanoparticle. Finally, I will introduce some work on plasmonic hybrid nanostructure for nanoelectronics. Electronic devices made from gold nanostructure is envisioned promise for next generation nanocircuits, since it can couple plasmonic excitation with electron flow. So one fundamental question is, can electron tunneling or transport be mediated by plasma field of nanoparticles? But difficulties and challenges remain. Besides short circuits and contact artifact, robust realization of active current carrying plasmonic nanocircuits has been challenged. Although methods used for plasmonics screen electronic fields, which prevents their use in the design of all metal nanoparticle circuitry. So far, almost most of work in this field focused on chemielectronic circuits. Less has been done to reveal the underlying ET mechanisms. Previously, when I was a postdoc in Weizmann Institute, I prepared LSPR-mediated gold nanoparticle monolayer planar junctions and observed the gold nanoparticle enhanced current transport through about 5 nanometer insulating layers because the small organic molecule introduced and also the planar junction configuration used. The result is quite questionable because the drawbacks of short circuit and contact artifacts remain. So to solve this, we prepared gold nanomembrane for diffusion limited aggregation at the air-water interface, and we bridge this membrane over 2 charge electrodes. We observed some plasmonic origin and response in the IVs of the junction, but the method of nanomembrane preparation is still lack of fine control and unstable. So we tried insulating gold nanoparticle with silicon nanoshell to prevent direct contact between gold nanoparticles and avoid short circuit and contact artifacts. The gold nanoshell can be made from few nanometer to tens of nanometer thickness. The pinhole-free nature of the particle has been undergone by at least 8 different methods. So we then assemble such nanoparticle into nanomembrane by self-assembling at all water interface. The robust nanomembrane can be transferred to cover on the 2 charge electrode. The nanoparticle has been well separated by the silicon gap, and the gap can be tuned by the thickness of the shell. Very interesting today in a typical junction prepared made of 12 nanometer gold, 1.8 nanometer silicon nanomembrane. We observed almost the linear response in RVs, but obvious step-like feature, which is a statistic of nonlinear electron tunneling. The RV response was quite in response well with the LSPR profile of the particle. In a control membrane made of 12 nanometer palladium and similar thickness of silica shells, there was no current transfer through the junction. We also did some simulation based on tunneling using WKB model. Even we use one row of nanoparticle as a simplified model, we found that the calculated current resources still a few order of magnitude lower than the value we measured. Note that there are almost more than 6,000 sequential tunneling events to across the gap. So that is amazing. So it reveals unusual electron transport in our systems. We first prepared the nanomembrane by increasing the shear thickness of silica and built into field-layered sandwich type junction. The devices has withstood harsh destructive test by gold amalgamation. So the contact artifact in our system can be ruled out. Very interestingly, we show a nonlinear response of IV behavior of our device. We revealed unusual super electron tunneling regimes with up to 25 nanometer insulating silica shells. So we also did some simulation and also performed size, shell thickness, and wavelength dependent IVs. The results show that the fitting equation was fairly similar to that of classic tunneling. But there is a fairly huge enhancement in tunneling properties. Summary: multifunctional compact hybrid nanoparticles with ultrathin gold nanoshell of varied functional core components and smart enzyme-plasmonic nanoprobe were reported and explored for multimodality imaging, sensitive biosensing, and single-cell studies. We also designed a series of plasmonic hybrid nanostructures and exploited plasmonic effects for catalytic applications, and we revealed a long-range plasmon field and plasmon-electric effect on catalysis. By insulating gold nanoparticles with silicon nanoshell and assembling them into ordered nanomembrane for plasmonic nanoelectronics, we revealed recently an unusual plasmon-enabled long-range ET regimes of the system. These findings will provide new insights into the understanding of plasmonic effects on sensing, catalysis, and electron transport, and will benefit for the design of novel biosensors and plasmonic nanocatalysis and nanocircuits. So I would like to thank our group member for hard work and collaborators at CIAC, Plasma Institute, and also UW Seattle.